All right. In this section, we're going to look at events and some other terminology, definitions, and things related to events. So let me just go ahead and adjust this real quick. It's okay. So let's go ahead and define an event. Definition here. An event is a subset of a sample space. Just a subset of a sample space. So consider the experiment of flipping a coin twice. Let's write out the sample space so we can, think about possible subsets then. All right, so there's our sample space, capital S. Flipping a coin twice. You're going to get heads and heads. Get heads in the first flip, tails on the second. Tails on the first flip and heads on the second, or you could definitely get tails and tails. There's 4 options. That would be our sample space. That would go ahead and that'll be our sample space. So let's go ahead and talk about some events that could happen. So we're going to go ahead and let capital A be the event with an equal number of heads and tails. Event with an equal number of heads and tails. Just that again real quick. There we go. So we tend to use capital letters to denote events, just like we use capital S for our sample space. But we probably want to name our event something other than S, because capital S is usually reserved for sample space. So common to start at the bottom of the alphabet there with A. It is a subset here. So let's take a look at equal number of heads and tails. Well, if you're flipping a coin twice, it has to be 1 head and 1 tails. So you could have the head tails component, or you could get the tails head element as well. And we just have 2 elements in event A. 2 elements in event A. Let's try something a little bit different. Suppose B is the event that contains the elements heads, heads, and heads, tails. Let's write out in words what this event could be, right? So let's go the opposite direction. Suppose we have heads, heads, and heads, tails. All right. So how could we state B in words? And there's going to be multiple ways to do this. All right. But just to try to get a feel for it. And I don't want something that's over specific, right? You don't want to say B is the event that has heads, heads, and has tails. That doesn't do anything, right? Let's try to be a little more generic than that. So what do we notice here that's in common between these elements? I would say that of the 4 that it could came from, these are the 2 that have heads first. So I would say B is the event of getting heads on the first flip. On the first flip. All right, so we should be able to try to translate these things back and forth, if you will, okay? Let's do part C here, one more, just to make sure we got this down. Let's say C. Let C be the event that has either heads or tails on the first flip. Either heads or tails on the first flip. And then we would say, well, okay, go ahead. Let's take a look. C then. Well, if you get heads on the first flip, you could get heads and heads. Or you could get heads and tails. If you got tails on the first flip, you could have tails and heads, or you could have tails and tails. Well, you might be saying, well, hey, hold on a second, Aaron. That's everything in sample space S, right? There's all 4 elements. That's fine. Technically, a subset couldn't be the whole set. Actually, it can be the whole set. So this is okay. This event is still contained in the sample space. Think about the other extreme. Rather than having all of the elements from the sample space, what if you had none of the elements? We refer to that as the null set. The null set or the empty set. Null set or empty set contains no elements at all. No elements at all. And this is denoted with a symbol. Looks like a 0 with a slash through it. 0 with a slash through it. Okay. Now, when you are working on anything maybe online, if you're in like a My Math Lab or something, or you should be looking for a math palette if you want to use the empty set. Don't just punch in 0. That's something different. There should be a button that you can locate for that symbol if needed. All right. Another definition here, okay? We're going to talk about 2 more things, and then we'll get to some more examples here. So let's talk about the complement of an event A. Complement of an event A with respect to S. With respect to S. The complement of an event A with respect to S is the subset of all elements in S. Subset of all elements in S that are not in A. Are not in A. And this is denoted in a variety of ways depending on the discipline or book you're using. A prime for A complement, or they'll do A with a C up there in the superscript for A complement, or sometimes A bar for A complement as well. Either way, just fine. I'll probably use, I think we'll be looking at the A prime notation for A complement here. And then this notation is the intersection of 2 events. Intersection. Intersection of 2 events that contains the intersection of 2 events, A intersect B, the intersection of 2 events, and this contains all elements that are in both A and B. All elements that are in both A and B. Have to be in both there at the same time. Okay. Let's take a look at an example here. Suppose we roll a die once. Standard 6-sided die. We can go ahead and write out the sample space for that. You can get a 1, a 2, a 3, 4, 5, or 6. Looks good. Let's go ahead and define some events. Let's say A is all the evens. Let's say B is all the odds. And let's say C is the lower 3 numbers here. So a 1, a 2, or a 3. All right. Let's write out a few sets here. Let's say C prime. Let's see A intersect C. And let's go ahead and try to take a look at A intersect B. And let's see if we can get a handle on this, okay? I'd encourage you to pause the video and try to give this a shot on your own here real quick before we go over the answers. All right, assuming you've paused and taken an attempt at this, let's go through these then. C prime, then everything that's in the sample space S, that's the complement, but is not in C, well, that was going to be 4, 5, and 6. All the elements that are in S but are not in C. How about A intersect C? Well, what is an A? 2, 4, and 6 is 2 in C. Yes. Is 4 in C? No. And is 6 in C? No. So the only element that's in common between both A and C is 2. So when you have that single element, you just put it in squirrely brackets just like that. And how about A intersect B? If we look at 2, 4, and 6, 1, 3, and 5, they have nothing in common. So this is the empty set. This is the empty set. When two sets, A and B, the intersection is empty, we say that these are mutually exclusive. Mutually exclusive. Mutually exclusive or disjoint. Disjoint. Two sets are disjoint if their intersection is empty. Another definition coming up for you here. If we have the intersection, some of you might be thinking, well, if we know the intersection, where is the union? And that is next. A union B. That notation, that is the union of two events. The union of two events containing all of the elements that belong to A or B or both, containing all of the elements that belong to A, that belong to A or B or both. That is notation for the union. All right. And it's at this stage that I want to introduce a strategy for visualizing some of these set operations, intersection and union. And that is, of course, the Venn diagram. The Venn diagram. Okay. Let's take a pretty standard Venn diagram picture. And let's see here. So I'm going to go ahead and call this one A. This is B. And let's just throw in a third here to make things interesting. Let's throw in C here. Okay. So the Venn diagram, you should have some outer universe. This is our sample space S. So I'll put S on the outside here. Okay, and let me see what's happening. There we go. S looks good. And we've got quite a few different regions here. All right. And I'll just try to connect that a little bit better there. So I'm going to go ahead and inside out number these regions. 1 is this region that's bounded there on all sides. And then 2, 3, and 4. Let's do 5, 6, and 7. And no, that is not all the regions. Do not forget about region 8 outside of all those sets, right? We can talk about what that is in a moment. And let's use these numbers here to identify what is in, well, let's use these numbers to identify what regions would be associated with which operations. Let's start out with these first 3. A intersect B, B intersect C, and B prime intersect A. Which regions are associated with these? Okay. A and B. A intersect B. So what regions are associated with A intersect B? That would have to be regions 1 and 2. Both in A and B at the same time. That would be 1 and 2. That would be numbers 1 and 2, right? That would be this area right here. That would be your A intersect B, okay? How about B intersect C then? that would be 1 and 3. 1 and 3. B prime intersect A. What would B prime intersect A be? So not B prime is everything that's not in B, and we want to be intersected with an A. Not in B and intersected in A. So region 7 is in A, not in B, and so is region 4. So we'd be looking at region 7 and 4 for this one here. And I'm just highlighting this just to help kind of visualize. Right? 1 and 2 don't make this cut. 1 and 2 don't make it. I suppose I can do 4 and 7 if I want to do that first here. 1 and 2 don't make the cut here. Oh, problems with the pen. 4 and 7. It's not going to be 1 and 2 because those are in B as well. All right, let's try some more. How about A union C? A union C, that's everything in A or C or both. So that would be 1, 2. Let's just do, well, let's see here. 3, that's in region C. 4 is in both of them. 5 is in C. 7 is in A. 6 is not in either, neither is 8. So that is it. How about A intersect B intersect C? Let's see if we can extrapolate what we know with our definitions on intersection. If you have to be in A intersect B and you have to be in C, then you got to be in all three at the same time. That is just region 1. How about A union B intersect C prime? A union B intersect C prime. So you have to be in A union B. So what are our options here? A union B, that would be 1, 2, 3, 4, 6, and 7. Which of those are not in C? 2 is not in C, 6 is not in C, and 7 is not in C. Okay. Good. So I will leave it at that. Oh, I was going to talk about what region 8 would be looking here. So if you wanted to do something like, how could we do this? We could do just A or B or C complement. Everything that's in A or B or C, and then you take not that, you take the common of that. That would be region 8. That would be region 8. Okay. So Venn diagrams are very nice, very useful. There are several important results that can be verified that are often easiest actually to be proved using Venn diagrams. Several results can be verified using Venn diagrams. Using Venn diagrams. And I'm going to share with you 2 common ones that I want us to be aware of. The first are DeMorgans laws. And DeMorgans laws are the following. The following sets are equivalent. A intersect B complement is equal to A complement union B complement. And A union B complement is equal to A complement intersect B complement. Those are DeMorgans laws. That is the first law that I want us to have in our back pocket, potentially. And this is somewhat intuitive, actually. You can sort of look at this as if you were to try to distribute the complement signal into the parentheses there. You get the A prime and the B prime, and what you do is you would actually sort of take the complement of the intersection symbol. Loosely speaking, you might think, well, the opposite of intersecting would be union, potentially, right? And so there's some sort of ways to help remember that. Same idea when you go from A union B prime to show that that is equal to A complement or B complement. But if you're not sure, take a look at what regions you think would satisfy the left-hand side of this equation, and then separately take a look at the regions that you think would satisfy the right hand of the equation, and you would find that those regions should be the same. The other one is the distributive laws. Distributive laws. Distributive laws are things like if you want to do A intersect the union of something. So say we want to do A intersect B union C. We can distribute this intersection. It'd be A intersect B or A intersect C. Or A intersect C. And then the other distributive law would be distributing the union. A union B intersect C is equivalent to A union B intersect A union C. The distributive laws. The DeMorgans laws and distributive laws are two things I do want us to try to be familiar with, potentially as we move forward. Again, I'm not asking you to verify this right now, but this can be very easily done using a Venn diagram here. Take a look at the left-hand side on its own and identify the regions that are associated with that. Then take a separate diagram and look at the right-hand side on its own and look at the regions that would be associated with that. If you numbered your regions the same, you should find that the same numbers are in both left-hand side and the right-hand side, and that would be a way to show they are equal. All right. That's going to do it for us here in this video at the end of this section. If you do have questions, please post those in the discussion thread below. Otherwise, we will see you in the next video.